We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that. We're now in the initial stages of the next revolution. We're talking about a new generation of computers, the ultimate computer, a computer that computes on atoms, the ultimate constituents of matter itself. The question is, who's involved in this race to perfect quantum computers? And the answer is everyone. All the big players are part of this race because if they're not, Silicon Valley could become the next Rust Belt. Also, anyone who's interested in security is interested in quantum computers. They can crack almost any code that is based on digital technology. That's why the FBI, the CIA, and all national governments are following this very closely. Quantum computers will change everything. The economy, how we solve problems, the way we interact with the universe, you name it, quantum computers will be there. I'm Dr. Michio Kaku, professor of theoretical physics at the City University of New York, and author of Quantum Supremacy, about the rise of quantum computers. You see, computers have gone through three basic stages. Stage one was the analog computer. So 2,000 years ago, there was a shipwreck. And in the boat that sank was a device, and when you brushed away the dirt and debris, you began to realize that it was a machine of incredible complexity. It was, in fact, the world's first analog computer, and it was designed to map the motion of the moon, the sun, and the planets to simulate the universe. But as we primitive peoples became more prosperous, we had to count things. Count how many cows you had. Count how much profit you made. Analog computers could be based on sticks, bones, whatever it took to count. So this went on for thousands of years until finally we reached the work of Charles Babbage. He creates the ultimate analog computer with hundreds of gears and levers and pulleys, and by turning the crank, you could then calculate longitude, latitude, you could calculate interest rates. It was very valuable to have an instrument like that for the banking industry, for commerce. Then World War II comes along. Babbage's machine is simply too primitive to break the German code, so the job was given to mathematicians like Alan Turing. Alan Turing was the one who codified a lot of the laws of computation into what is called a Turing machine. And of course, it's digital. Now, the digital revolution is based on transistors. It operates on zeros and ones, at the speed of electricity. Every digital computer is a Turing machine. The next step beyond digital computers is the quantum era. Richard Feynman was one of the founders of quantum electrodynamics, but also a visionary. And he asked himself a simple question: how small can you make a transistor? And he realized that the ultimate transistor is an atom. One atom that could control the flow of electricity, not just on or off, but everything in between. We have to go to quantum computers, computers that compute on atoms rather than on transistors. Transistors are based on zeros and one. Reality is not. Reality is based on electrons and particles, and these particles in turn act like waves. So you have to have a new set of mathematics to discuss the waves that make up a molecule. And that's where quantum computers come in. They're based on electrons. And these electrons, how come they have so much computational power? Because they could be in two places at the same time. That's what gives quantum computers their power. They compute on not just one universe, but an infinite number of parallel universes. At the fundamental level, quantum mechanics can be reduced down to a cat, Schrödinger's cat. Let's take a box. In the box, you put a cat. And the question is the cat dead or alive? Well, until you open the box, you don't know. It is alive and dead simultaneously. It's in a superposition of two states. In other words, the universe has split in half. In one half, the cat is alive. In the other universe, the cat is dead. That's the basis of the quantum theory, that until you make a measurement, the cat can exist in both states simultaneously. In fact, in any number of states simultaneously. The cat could be dead, alive, playing, jumping, sideways, sick, any number of states. Now, why am I mentioning this? Because this summarizes the power of quantum computers. Quantum computers compute on parallel universes. That's why they are so powerful. So how much faster is a quantum computer over a digital computer? In principle, infinitely faster. When we talk about digital computers, we can measure their power in terms of bits. For example, spin up, spin down, zeros and one, would constitute 1 bit. For a large digital computer, we're now talking about billions of bits that are modeled by transistors. Except now, quantum computers talk not just about spin up or spin down, but everything in between. That's called a qubit. 1 qubit represents all the possibilities of an object spinning between up and down. Thousands of qubits can now be modeled with the latest generation of quantum computers. Eventually, we hope to hit 1 million. And so we're talking about exceeding the power of ordinary digital computers. That's called quantum supremacy. It is the point at which a quantum computer can outrace and outperform a digital computer on a certain task. We passed that several years ago, but we want a machine that could exceed the power of any digital computer. We're not there yet, but we're very close to it. The number one problem facing quantum computers is the question of decoherence. Everything is based on particles like electrons, and electrons have waves associated with them. When these waves are vibrating in unison, it's called coherence. And then you can do calculations of a quantum mechanical nature. But if you fall out of coherence, then everything vibrates at a different frequency, and what is that called? Noise. You have to reduce the temperature down to near absolute zero, so everything is pretty much vibrating slowly in unison. That's difficult. Now, nature solves this problem. It is the basis of all life on the earth. Photosynthesis, for example, is a quantum mechanical process. Mother Nature can create coherence at room temperature. Amazing. A flower can do calculations that our most advanced quantum computer cannot. Mother Nature is still smarter than us when it comes to the quantum theory. So let's face it, there are hurdles affecting the growth of quantum computers, but they pale in comparison to the benefits that may be unleashed by quantum computers. We're talking about opening the floodgates. Take a look, for example, of food supply. The green revolution that allows us to feed the population of the world is slowly coming to an end. We're trying to use quantum computers to unlock the secret of how to make fertilizer from nitrogen. Take a look at energy. Quantum computers may be able to create fusion power by stabilizing the superhot hydrogen inside a fusion reactor. And take a look at medicine. You realize that life is based on molecules. Molecules that can create Alzheimer's disease, Parkinson's disease, cancer. These diseases are beyond the reach of digital computers. But hey, this is what quantum computers do. We'll be able to model diseases at the molecular level. And that's why we hope to cure the incurable using quantum computers. We're talking about turning medicine upside down. My personal hope for quantum computers is that we'll be able to create a theory of the entire universe. The theory that eluded Einstein, the theory that would explain black holes and supernovas and galactic evolution. But the equations are so complex that no one has been able to solve them. Perhaps they'll be solved in the memory of a quantum computer.
To learn even more from the world's biggest thinkers, get Big Think Plus for your business.